Recitation problem 5. A small ball of mass m and radius r rolls from rest and without slipping along the loop apparatus shown in the diagram. Determine the minimum height h from which the ball can be released and still negotiate the loop. Express your answer in terms of the radius of the loop, capital R. Assume that the radius of the loop is much greater than the radius of the sphere. As usual, let's put together the free body diagram for the rolling sphere. The sphere is under three forces: the normal force, which is perpendicular to the surface of contact, the weight mg, which acts straight down, and finally, the static friction force, which acts up the incline and parallel to the surface of contact. We know that the work done by the normal force equals to 0 because the normal force is at all time perpendicular to the displacement of the ball. The work done by the static friction force is always 0 because static friction forces do not do work. As a result, the only remaining force is the mg, which is a conservative force. Conclusion: the work done by the non-conservative forces, which are Fn and the friction force, equals to 0. This conclusion allows us to use the conservation of energy relationship. The Ke initial plus the Pe initial equals the Ke final plus the Pe final. The initial position is the release point because we have interest in solving for the release height. The final position is the top of the loop because there is an important known information that is presented in a hidden form, which is the speed of the ball. To expose the speed at the top of the loop, we need to use Newton's second law. The sum of the forces acting on the ball equals the mass times the centripetal acceleration. The two forces which are acting on the ball at the top of the loop are mg and the normal force, and both of them are acting straight down. Detailing Newton's second law, we obtain the normal force plus the weight mg together equals the mass times the centripetal acceleration. Notice that both forces are pointing towards the center of the loop, therefore both of them are going to have positive components. Along the y direction, which is the straight down direction, we have Fn and mg, both of them positive, equal m times the centripetal acceleration. The normal force at the top of the loop equals 0 because the ball at that moment is about to lose contact with the surface. This is due to the fact that the ball is released from the minimum height that allows it to go around the loop. Detailing the equation a little more, we obtain mg to equal m v squared over r, which is the radius of the loop. Notice that the mass is going to cancel out. Isolating the speed squared, we obtain g times r. Now we are ready to go back to the conservation of energy equation and detail it. The Ke initial plus the Pe initial equals the Ke final plus the Pe final. The kinetic energy initial is 0 because the ball is released from rest. The potential energy equals to mgh, where h is the height that we are trying to solve for. The kinetic final is in two forms: the translational kinetic energy, 1/2 mv squared final, plus 1/2 I omega final squared, plus the potential energy final, which is mg times the diameter of the loop, which is 2 times r. Detailing this equation a little further, we obtain mgh equals 1/2 mv final squared plus 1/2 times the moment of inertia of the ball, which is 2/5 mr squared, times the angular speed squared, which is equal to the speed final squared divided by the radius of the ball squared, plus 2 times the mass times g times r. Notice now that the mass is a common factor and it's going to cancel out. Notice also that the r squared here is going to cancel out with the r squared here. These two cancel out with the half. Therefore, the equation is reduced to the following. G times h equals 1/2 v final squared plus 1/5 v final squared plus 2 times gr. gh equals, the common denominator between the half and the fifth is 10. Therefore, 1/2 v final squared plus 1/5 v final squared is going to equal 7/10 v final squared plus 2 times gr. This v final squared is the one that we solved for earlier, and it's equal to g times r, where r is the radius of the sphere. Making the substitution, we obtain gh to equal 7/10 times gr plus 2 times gr. Clearly the gravity g cancels out, and the final expression for the height h is going to equal 2.7 times the radius of the loop.